Hi everyone. To start chapter 7, we will start with 7.1 Cartesian vectors. So what is a Cartesian vector? So a Cartesian vector is, let's say we're looking at one vector here, QR, a line segment that connects 2 points together on a Cartesian system on a grid that also has a direction to it. So meaning that it has a direction, one end has to have an arrow, right? So that would be a Cartesian vector. So for the points P1, let's say Q is P1. So that's a coordinate point of X1, Y1, right? Just meaning the X value of the first point, the Y value of the first point, and P2, let's say, is R. So that would be X2, Y2 point on the coordinate plane. Then my Cartesian vector of P1, P2. To calculate that, that would be equal to, I subtract my X's, and I subtract my y's, my differences in my x's and my differences in my y's. Though I have to start with the coordinate from P2 and subtract P1 from it. Okay, so it has to be the second point first minus the first, and the second point first minus the first. And that is the Cartesian vector with the tail at P, right? And that's y, and the head at 2. So you start with the head minus the tail, the head minus the tail. Okay, so let's do an example here. Yeah, so P1 is always, just so you know, let's maybe write this down. P1, just because I can't fit it in there maybe. P1 is where the tail is. And P2 is where the head is. So let's go back to these points and actually calculate it. So this point is actually on, if you were to zoom in, the point -3 on X and down 2. So that's where the tail is of my Cartesian vector. And the head, the very tip of the arrow there, is at 2 and 4, right? So this would be my X1, Y1, first point, the tail. This would be my X2, Y2, second point, the head. So then according to this, to calculate the Cartesian vector of QR, that's equal to subtract my x's starting with the head, starting with the second point. So X2 minus X1 to subtract -3, so double negative, comma, subtract my y's, right? In this way, in this fashion, saying starting with 4, then subtract -2. And then we end up with the Cartesian vector QR is equal to 5, 6. So just note here, can you see how these are square brackets, right? And within them I have like this coordinate point was round brackets. So we always use round brackets to identify coordinate points way back in, let's say, elementary school even. But now we're going to use square brackets to identify a vector. So because it's a square bracket, then I'm understanding that that is a vector, a Cartesian vector. And basically what this 0.56 is saying is that to get from Q to R, because that's where the tail is, to move towards the head, to get there, I have to move 5 to the right, 5 units to the right, and I have to move 6 units up. So my horizontal first, and then my vertical. So along my X, right, because X coordinates first, and then up along Y. And that's basically what that's saying. So it's kind of like a slope. So like the slope of this line, right, rise over run would just be Y as the numerator. So the slope of this line would be 6/5. Right? Whereas a position vector, I can erase everything, is a Cartesian vector whose tail, the tail is positioned at the origin, 0, 0. So a position vector just means that its position, its initial position is at 0, 0. And the tip is positioned at wherever it is. So we just said here at point P, which has the coordinate points of A, B, let's say. So my position vector, OP, so again, you always start it with the tail to the head when you label the vector, right? OP is equal to square brackets, right? So moving along A first, what are my horizontal units? How many am I moving to the right and how many am I moving up? My vertical units would be B. Okay, so how does a position vector, let's say, compare to a Cartesian vector? They're the same thing, But let's say I was to move Q, the tail, up into the origin at 0, 0, then this whole vector would just shift, right, more up into the first quadrant. So my tail would have to move to 0, 0, and therefore my head would have to move as well. But this is 5 units to the right and 6 units up. We're saying here, let's use the same exact vector. So move it 5 units to the right and 6 units up. So literally these vectors are the same. The only difference is that it's positioned at the origin. So for this Cartesian vector from above, we're going to call this vector OP, the position vector. 5, 6 is the position vector. So it's the exact same vector, just positioned at the origin. So we call it the position vector. Okay. What is a unit vector? So unit usually breaks something down into one, right? So it's the building blocks of our Cartesian vector, and it has a magnitude, a length of 1. So for example, if I were to just call these vectors vector I and vector j. So let's say this vector I has now it's not like a coordinate point, right? It's components of the vector, the horizontal component because x is first along the x-axis, and the vertical component because y is second. So this would have the components of 1 and 0, meaning that vector I is moving 1 to the right and no movement up or down. It's not moving up or down. So it's just moving 1 to the right. So if I'm moving 1 to the right, then I'm moving horizontally, has a magnitude of 1, then that's my horizontal unit vector. Whereas if vector j, right, has no horizontal movement at all, but it's moving 1 unit vertically up, right, then it's moving up 1 only, a magnitude of 1, then that would be my vertical unit vector then, right? So these are special unit vectors that have their tails at the origin. So back to that position vector, OP, that was 5, 6. It can be written in terms of vector I and vector j. So again, we're talking about 5 horizontal unit vectors of I, and then we're going to add to that 6 vertical unit vectors of j. So what I'm saying here is that I'm moving, it's just a bright color here, 5i, 5 horizontal. So I'm moving 1 unit vector, 2 unit vectors, 3, 4 with arrows, 5. And then I'm moving up 1, 2, 3, 4, 5, 6. So you can see how we can take each unit and turn it into whether it was a Cartesian vector or a position vector. What is the magnitude of a vector? So we already know the magnitude is the length of a vector, right? But how do I figure out the magnitude of a Cartesian vector? So if I had a Cartesian vector P1, P2, that's on a coordinate plane. So obviously P1 is the first point, X, Y. P2 is the second point. To figure out the length of a vector, it's the exact same thing as figuring out the length of a line segment, right? Because it still looks like a line segment on there. It just has a tail and a head, a direction to it. But that doesn't matter when we're figuring out the length. So it's just the square root of, again, subtract my change in my x's, subtract my x's and square them, and then add, be careful that it's adding in the middle, and then my difference in my y's, subtract my y's and square them. So these are just 2 different ways of relaying the same information. So let's use that position vector where O was the coordinate point 0, 0, right? And P is the component parts. Well, and I guess we also have the coordinate because we have it labeled here on the grid that it is the 0.56 as well. So it can be in rounded brackets. Okay, so we have the position vector OP equals 5, 6, where we have the coordinate 0, 0, 0 along O and 0.56 along P. So the magnitude, to find the magnitude, right? That indicates magnitude, like the absolute value symbol there. I get my differences in my x's and my differences in my y's. So again, it's the second x first, 5 minus 0 squared, and then 6 minus 0 squared. So that's just 5 squared plus 6 squared, which ends up being the square root of 61. So simplified, if you could leave it like that. I don't know what the textbook is going to say, you know, if it ends up being 7.8 units for vector OP, or if they sometimes will leave it in radical notation. Either one, just know to check one if your answer is different than what it's displaying, okay? So if we were to do, we also said that this position vector is like the same length, the exact same vector shifted from its original, let's say, QR position. So let's use QR and just do one more example with these points, which I'll copy out for you here on this second page, just to prove that it's the same length, right? And just to practice this one more time. So let's say I have the figuring out the magnitude of the Cartesian vector QR. So I have my points. Q was, I wrote it down here, -3, -2, and R is 2, 4. So again, I should write out that this is x1, y1, just to make sure, and x2, y2, just saves any errors. And my formula is to do the square root of my difference in my x's, x2 minus x1 squared, bracket, plus y2 minus y1 squared. So to subtract my x's is 2 minus -3, which we already did on the previous page, square it, 4 minus -2, square it. So that's 2 plus 3, so that's 5 squared. 4 plus 2, that's 6 squared. Well, now it's looking the same as here. So I'm just going to skip and go right down to it being the square root of 61. Okay, so just proving that they are the exact same vector, right? Just whether it was at 0, 0 being the position vector, or otherwise it's just called a Cartesian vector. Okay. So what if we were adding vectors? Add the horizontal and the vertical components if I'm adding two Cartesian vectors together. So for example, if I were to have the vector u, which has the, again, these are square brackets, which has the horizontal component u1 and the vertical component u2, and then I have vector v, which has the horizontal component v1 in the horizontal direction, and then the vertical direction v2. To add those Cartesian vectors together, adding vector u and vector v together, I would just add my x values, u1 plus v1. And it doesn't matter to go the second plus the first, but if you want to just maybe even go in that order, v1 plus u1, then you're always going in that order. You won't accidentally forget when it's up above where it has to go second minus first. And then comma, add your y's together. So again, you might just want to do v2 plus u2, just to make sure you're always doing it in that order. And then to subtract vectors, just to move this up, you're just going to add the opposite, just like we have in the past. So add the opposite of the horizontal and add the opposite vertical components. So again, for vector u, horizontal component, vertical component, vector v, horizontal component, vertical component. If I'm subtracting them, I would subtract u1, the x value, minus v1, subtract the first position minus the second position. Now, because I'm subtracting, I'm doing the opposite. And then take the first y position, subtract the second y position. Okay. And then for multiplying a vector by a scalar, so multiply the scalar value of both the horizontal and the vertical components. So just saying again, if I have this vector u that has a horizontal and a vertical component, and I have this scalar k, I'm going to call it a constant that belongs to the set of real numbers. I have my vector u, it's just multiplied by 2, by -6, by a half, by anything, right? By a scalar. And then I'm just taking the constant of k, the scalar, out, and it's being multiplied by the horizontal component and the vertical component. So just distributive property here, right? I just take that k value and multiply it in. So then I have k times u1 and k times u2. And we'll do an example of that. In chapter 6 that we just did, a geometric vector, if you remember the force F, the F vector, was written in terms of the horizontal component that we made up of the rectangular component and the vertical component, right? So my horizontal component of the force vector was the force vector multiplied by cos theta, and the vertical component of the vector was the original F vector multiplied by sine of theta, right? And again, theta being the angle your vector makes with the positive x-axis, if you want to write that down. The angle we're talking about, right? We always have to start with the positive x-axis and we're moving in a counterclockwise position, right? So then as a Cartesian vector, vector F can be written as vector F is equal to, right? The magnitude of vector F times cos of theta, comma, the magnitude of vector F times sine of theta. Where again, just what I had just said, where theta is the angle that it makes with the positive x-axis. Okay, so I have to put my horizontal component first, right? Because that's x, so that would be why this horizontal is first, and then in the y position would be my vertical. So we're going to be using these now. Collinear vectors. Vectors that are the scalar multiples of one another, okay? So scalar multiples of one another, we've already gone over a scalar multiple. Collinear unit vectors though. So it's a unit vector, but the difference is that it's collinear. So vectors that are scalar multiples of one another and have a magnitude of 1, right? Just because of the unit part. So collinear could be moving in the same direction or opposite direction, but it's also parallel to the original vector, let's say. They're parallel to each other. So let's go over a couple examples. Example 1, if I have the point C, so this is a point, rounded brackets at 6 and -2, and I have the point D at -1 and 5, figure out the following. What is vector CD? So first I would probably label, if this is my first point, that this is x1, y1, and that this is x2, y2. So then to figure out my vector CD, I'm finding vector CD, the tail is at C, right? And the head is at D. It is always in that order. So what I'm going to be doing is subtracting my x values and then subtracting my y values. Remember, second minus first. So -1 minus 6, comma, y2 minus y1, 5 minus -2. So then that would be -7 and 5 plus 2, 7. So there we go. That is my vector CD, has that horizontal component and that vertical component to it. So what if I now want to find the magnitude, right? Has the absolute values around it, means I want to find the magnitude, the length of CD. So I've got the formula there. Neither one of these are 0. So I've already subtracted it in A, right? I would be subtracting my x's, x2 minus x1 squared plus y2 minus y1 squared, but I already have my x's subtracted in the answer and the y's subtracted in the answer. So why not save time and say, okay, my x's subtracted was -7 squared plus my y's, the difference in my y's was 7 squared. So -7 squared is 49. So I'd have 49 plus 7 squared, 49. Which is almost like 50 plus 50 minus 2, 98. And again, depending if the answer is left at the square root of 98, it might be written as, we have perfect square 49 times 2 is 98. So 49 times 2, the square root of 49 is 7. So then that would be 7 root 2. Or if I just plug that into the calculator, it could also be 9.9 units. So it just depends on how the answer is written out. That's a 7. I feel like that's a little messy. 7 root 2. Okay, so that's my length. My length is 9.9 units or 7 root 2 units, or the square root of 98 units too. It could also be your final answer. So what if I have a scalar multiple of CD? just to write out that's what that is, right? It's vector CD, Cartesian vector CD multiplied by -2. So scalar multiple of CD. Then I would literally just take -2, and I already know what my vector CD is. -7 and 7 are my components. And then again, I just use distributive property to distribute in. So then I would have -2 times -7, keep your square brackets because it's components, right? Is +14, and then I would have -14. So the components are horizontally 14, and then I'm vertically going down to the right 14, down 14. Okay. I'm gonna try, I think I'll be able to fit this in without moving. And then I'm just looking ahead. I will do example 2, and then I'll put 3 and 4 on another video again, just to break things up. If you're at home watching, only watch whatever half that you need to, makes it convenient, or in terms of breaks for you or for I. A vector collinear. So I'm looking for a vector that's collinear with vector CD, right? And has a magnitude of 1. So I'm looking for a collinear unit vector, right? So it has to go in the same or opposite direction. Like I said before, it's a parallel vector. We know that the magnitude of CD itself, just to check, is not 1, right? So that's not my unit vector, right? It's 9.9, which is almost 10 units long. So it's clearly not the unit vector. So we need to find a collinear vector then that would have a magnitude of 1. I'm just seeing there is a longer way of doing this, but I think I'm just going to go right to showing you guys the shortcut, because once I show you the long way and the short way, you're just going to go right to the short way anyways, right? So the magnitude needs to be 1, but I do know that vector CD, so I know that vector CD has the components of -7 and 7 from up here, right? So basically the formula for figuring out a vector that's collinear and has a unit of 1 would be 1 over the length of vector CD multiplied by its components, the components of CD, multiplied by -7 and 7. Okay, so that's going to be equal to 1 over, what's the magnitude of CD? That's over here. So whether I put square root of 98, 7 root 2, 9.9, I'm just going to put, you'll see why, maybe I'm going to put 7 root 2 and then multiply that by the components, -7 and 7. So then again, this is one like scalar multiple. This is a value of k. It's getting multiplied in. So when I multiply that in, I have -7 on top over 7 root 2, comma, 7 times 1 is 7. And that's like over 1. So 1 times 7 root 2 is 7 root 2. And then these, just to say, the 7s would nicely cancel out and become 1s. So then I'm left with a -1 over root 2 and a +1 over root 2. So therefore, a vector collinear with, therefore, a vector that is collinear with vector CD is k, the scalar multiple, k times the vector CD. So my k value are these two values. So I'm going to use the positive, let's say, 1 over square root of 2 times vector CD, which is -7 and 7. Which I would get down to my answer of, again, -1 over square root of 2, and then 1 over square root of 2, right? Because I'd have the -7 and the work that I've already done here. So I would have an answer of positive and negative 1 over square root of 2. And that's only plugging in the positive value. Then I can also plug in the negative value as well. But I can choose to just do 1. So the vector collinear with CD that has a magnitude of 1, because we have 1, that's why 1 was in our equation, is the scalar multiple, would be, again, the work that I've already done here, I would end up getting a value of my horizontal component would be negative 1 over square root of 2 from here to here, and 1 over square root of 2, which would be from this step to this step. So that would be the horizontal component, and that would be the vertical component of a vector that would be collinear with CD. Okay, so moving on to, I said I would do 2. Write a Cartesian vector for each of the following. So I have a force of 100 newtons with a bearing of 310. So that would be a true bearing then, right? So let's draw that in. Not too big, just off to the side. So if I have my vector, right, starting north, 310 would be 90. Another 90 would be 180. Another 90 would be 270. So 270, 280, 290, 300, 310 would be another 40 degrees. So that's basically a 45, right? Basically like that. Again, I need to indicate that starting here, and I should put north on there, that angle is 310 degrees. That's from the north clockwise. But again, how are we using our angles when we're doing Cartesian vectors? The angle that we need is starting from the x-axis, remember, going counterclockwise. So we have to calculate that. So the vector we want is going from the x-axis, right? Going counterclockwise to where our vector is. So we want this angle. So we know that that's 90. So let's say our angle, 90 plus what? 90 plus, well, again, this was 90, 180, 270. So from 270 to 310, remember we counted, was 40 degrees. So if this was 40 degrees, then the rest, 90 and 40, would make 50 degrees in here. So 90 plus 50 is 140 degrees. So that's the angle that we want to work with, because we have to start from the x-axis, the positive x-axis, and we're counterclockwise. So write a Cartesian vector. So for our Cartesian vector, we want to know the horizontal and vertical components of this vector. So we're using that formula that was just at the top of the flip side of this page, the previous page. So our vector F is equal to square brackets for our components. Our vector F, if you remember, times the cos of theta, because that was the horizontal movement. And then the magnitude of vector F multiplied by the sine of theta, because that's our vertical component. And we can write that down. This section, if I can fit that, is the horizontal. And this component here is the vertical. And again, x and y. X is horizontal, right? Y is vertical. And then we just plug in what we have. So that would be equal to the square bracket of what is our force is 100 times the cos of the angle that we want was 140. That's why we had to calculate it, right? And then the same 100, but we just change it to sine of 140. I gotta write smaller. So 100 cos of 140, you might be able to plug that directly into your calculator or figure out the cos of 140 and then multiply by 100. So please double check this. On some calculators I've seen, I didn't get the right answer when I checked on another calculator. So every calculator is different how you punch it in, right? So you should get negative 76.6 and then 64.3, which is positive. So again, if we think about it, if I start at the origin, if I was to move, this is left and right. So left, negative 76.6 horizontal units, and then up 64.3 units. So I'm moving horizontally a little bit more than I'm moving vertically. I end up at the head of my vector. So that makes total sense, right? Let's try one more. So again, sorry, this is all part of A. Let's draw our vector. Sorry, I thought that was a straight line. So this is a quadrant bearing. So I have a force of 25 newtons that has a bearing of south to east. So I should put in my bearing directions here, north, south, west, east, draw my vector. So I'm starting south and I'm moving east, south to east 30 degrees, which means not quite 45, a little bit less. So again, if this was, let's say 45, I'm going a little bit less, somewhere around there. And I'm going to do it maybe a little bit bigger than you would just in terms of being able to draw things in here, right? So I need to draw in the angle that they gave us. The angle they gave us was south, starting south and going in the east direction 30 degrees. Is that the angle that I want to use though? And that's a force of 25 newtons, I should say. But the angle that I want, be careful, is starting east. Starting on the x-axis positive and moving counterclockwise all the way around to there. I have to figure out what that is. So let's say again, our angle would be starting here is 90, another 90, 90 plus 90, plus another 90, and then what is it gonna be? So 180 plus 90 plus that chunk was 30. So that's easy enough, right? Because that was 30 degrees. So 270, 9, 18, 27 plus 30 is 300 degrees is actually the angle that we are going to use. So we are going to do, I'm not going to write out the formula again. I'll just say that it is the force 25 multiplied by the cos of our angle 300. And then comma the force of 25 multiplied by the sine of our angle 300 and close my brackets. And then again, be careful with your calculator. 25 times the cos of 300, you should have a positive 12.5. And 25 times the sine of 300 is actually a negative 21.7. But let's go back and see if that makes sense, right? So if I start at the origin to get to my Cartesian vector here, it's telling me that I would go to the right 12.5. And then I would go down 21.7. So right and down makes sense to get to the head of my vector. And it should be that the horizontal part is a bit shorter than the vertical part. So again, maybe my drawing isn't great there, but it does look like, looks like the vertical part is longer, right? So like I said, 3 and 4, let's just split up and put into another video.